So welcome back to the video series on BJTs. In this video, I'm going to teach you how to identify the different operating regions of a BJT. Now, so this is an Icvce graph. You'll be confused like, whoa, why are there so many lines? Now, all these lines basically tell you what value of the IB I'm using, okay, the base current. So based on the different base current, I'm going to have different graphs that gives me different collector current and how it looks like when I increase the VCE, which isn't much. Okay, so what you do need to know, is the three regions: saturation, active, and cut-off region. Basically, all you need to know is that when it acts as a switch, remember a BJT turning on, off, it toggles between the saturation region and the cut-off region. So when I have the proper base resistor and I input in the input voltage, by right, it's going to toggle between the cut-off and the saturation, cut-off, saturation, cut-off, saturation. So off, on, off, on, off, on. Okay, so that is the saturation cut-off region. Remember, it's just going to be very simple. They're going to draw it for you over here. Remember, cut-off, saturation. I'm sure you can do that. So what is this active region? Active region is when it acts. This is the part where we want it to be when we are using the BJT as an amplifier. And so the active region is a very big region. It's a huge region over here. Where's the best part to find to work the BJT as an amplifier? Is it this part? Is it this part? Is it this part? What value of base current do I use? Where do I want my VCE to be? There's so many parts, right? Do all parts work the same? No. So what we need to do in order to find what is the best part, what's the best condition to work the BJT as an amplifier, is to draw something called a DC load line. So if I have a DC load line, what I want to do is to choose a point somewhere in the center of the DC load line. How do I get this DC load line? It's not in your syllabus. You do not need to know. I could teach you, but I don't want to further confuse you. Just know that magically a DC load line will appear, and the point that I want is the best point to work the amplifier, the BJT as an amplifier, is this center point, somewhere in the center, called the quiescent operating point. Okay? So remember, summarize. Three regions: saturation, active, cut-off. If I want it to work as a switch, I toggle between the saturation, cut-off, saturation, cut-off, on, off, on, off. And if I want it to work as an amplifier, I have to use the DC load line. It's going to magically appear for you, don't worry. And I choose the nice center point over here. So with this nice center point, so basically I want the IB to be 30 microamperes. I want my VCE condition to be somewhere about 8, and I'll get my IC to be somewhere about 3 milliamps. It's going to work beautifully as an amplifier for you. Okay? So that's all I'm going to talk about for the Icvce graph, because that's all you need to know. That's all you need to know for your level of studies. The next thing that I do want to talk about is something called a Darlington pair. So all this while I've been saying that we can drive whatever load we want to saturation, and we are going to light up a LED. Oh, sorry. Before we do that, you need to know that I can configure a BJT into 3 configurations: common emitter, common base, common collector. You just need to know that if the input is the base and the output is the collector, B, C, it's a common emitter. Okay, so if I have the input as an emitter and the output as a collector, I'm configuring it as a common base. So the pattern here is the input B, output C. The configuration is what's left, E. Okay, so you need to know how to recognize this. Okay, this is the input output. So the input is the base, the output is the collector, so common emitter. Okay, this is the most common one that we usually use. All right, so remember this. Sorry, now back to the BJT not driving it properly. So this is what I showed you. The BJT, by right, if I have an input here, I will have the base current flowing in here, and therefore I'll have a lot of collector current flowing through here, and whatever load I have will turn on and it will work beautifully. But that's sometimes not the case, because even though I feed in the maximum base, as much base current I have here, the maximum collector current is still not big enough to drive this fella into saturation. That means if it's an LED, it's not going to be properly lit up, it's not going to be full brightness. If it's a buzzer, the buzzing sound is going to be very soft. So it's not working at its maximum, right? Because the collector current is not big enough. So in order to boost up the collector current, what I can do is I can put two BJTs in this configuration, bang, bang, and this is called a Darlington pair. Okay, by putting a Darlington pair configuration, it's going to boost up, it's going to supercharge the collector current here by a lot. Okay, so that's the whole idea between a Darlington pair. You need to know how to draw this configuration. Remember how to draw. So you have to remember how to draw it. Okay, you need to know this next part is that, so if I have one BJT, the collector current is going to be the base current is going to be multiplied by the beta to give me the collector current. If I've got two BJTs, the collector current is going to be obtained by the beta square of the base current. So you can see immediately IC is going to be the beta square times of IB. So usually it's just beta, right? But if I have a Darlington pair, it's going to be square. So imagine if the beta value is 100, now with a Darlington pair, it's going to be 10,000. Okay? So it's going to be, instead of multiplied by 100, it's going to be multiplied by 10,000. Okay? So this is the configuration. Normal BJT, Darlington pair BJT, in order to increase the driving power to make the buzzer buzz at its maximum volume. Now, also please remember that yes, it's very good. It can increase the collector current, but there are some disadvantages. Go and read this. To summarize, because you have two BJTs, it's going to be slightly slower, so the speed is slower. There are two BJTs, that means the VBE is going to be bigger. So this is the VBE is going to be bigger, right? There, since there are two BJTs, the VCE is also going to be bigger. So the VCE is also going to be bigger. So these are the few disadvantages. Just know this. So this is how they show you the calculation. In order for this load to work, it works very nicely with 500 milliamps. But if you take the 100 microamps, you multiply it by 100, you find that it's only 10 milliamps. So you find that you only have 10 milliamps flowing down here. Not enough for the 500 milliamps. So whatever this is not going to work properly. So if I want a bigger collector current, what I can do is I can put two BJTs together in a Darlington pair configuration. Now the beta is not going to be 100, it's going to be 10,000. And if I take the 100 microampere input, I multiply by 10,000, I get 1 ampere. Now 1 ampere is definitely going to be big enough to drive it to saturation, because the original working current is 500, now it's 1 ampere. It's going to be 1 ampere now, so not a problem. So this calculation is a recalculation to find out what is the IC set. Okay, so what is the maximum current flowing down, the saturation current. Because don't forget, because we put two BJTs, right, the VCE changes. So once the VCE changes, the IC changes slightly, but it's a very slight change. Okay, by right, taking the two beta, squaring it, you will still definitely overcome the new IC or the old IC set. So that's not an issue. Okay, so go and try this example. Go and find out whether this Darlington pair configuration will drive it to saturation. Yeah, and practice. And I think this is about it. This is the information you need to know for BJTs. If there's any more questions, you can email me or you can ask me when you next see me. All right, so hope this has been useful.